Do you have a favorite place to read about the linguistic theory? Is there a good reference for that? Other than like traditional groups.
Yeah, probably it's good to go to the original papers, but there's some books on this.
Figured there would be too, but I'm sure. I mean, there's really good like lectures that you can find. Like Riquier has some good lectures.
Yeah, so Raphael is probably one of the experts on this. Yeah, I'm just trying to think. He doesn't really write books. Write survey articles. So we're half the class. If they're up too late last night. Anyway. I did stay up. After a while, like I said. Okay. Turn on the light. All right, so today what we're going to do is we're going to talk about GRT modules. So, all right, so the idea is the following. So, so GRT is an object, and I'll define it in a second, but basically GR is a normal subgroup scheme inside of GRT. And when you take the quotient of GRT with G, R, you get a copy of the torus twisted orthogonal. So the idea is that we want to look at the category of GRT modules, and these are GR modules with an additional TF. So when you look at mod GRT, so basically you know, we're looking at GR modules, so modules for the Frobenius kernel, and then we have the additional T action. And so the idea is that you want your module morphism to be T equivariant. So a GRT module is sort of a map from GR cross M into M, and everything in sight is acted on by T. So you want this map to be T equivariant. So roughly speaking, if you take G on M times M, then what you want is you want the following. So you want T on G times M. Okay, so T is in T. G is in GR, and M is in M. So basically, the idea is that you want this to be sort of, you want some compatibility. So this is T on G, T on G. Okay, and the T here is going to act by conjugation on G. Okay, normalizes G on. Okay, so the main idea is that when you have a GRT structure, you're basically putting a grading on it. So the idea is you basically look at graded. Okay, so not everything is graded. So we're only looking at a certain collection of GR modules, but these are GR modules that are sort of graded with respect to forms. Okay, so now what I'm going to do is I'm going to define this object GRT. So I'm going to talk about representations. For this category GRT, and I might as well do this too, what I call GRB. Okay, so the idea is fairly simple. So you have a Frobenius map. So you have a Frobenius map F, which goes from G to G. And now just iterate the Frobenius map R times. So F to the R is F composed with F. Now, what we know is that when you take the Frobenius kernel, it's just the scheme theoretic kernel of the Frobenius map iterated R times. So GR is the kernel of F to the R. So what I want to do is I want to sort of attach a torus to this. So what I'm going to do is instead of pull back F inverse of the identity, I'm going to pull back F inverse of the entire torus. Okay. So GRT is F to the R, the inverse image of the torus. So remember, this also goes from G to G. So I take my torus inside of here, maximal torus, and I just take the inverse image of that. And so you can guess what GRB is, right? You just take the Borel and then you just pull back the inverse image. Okay, so these are sort of scheme theoretic gadgets that you want to look at. Okay, so so what do we know about these things? So B gets mapped to B, right? Under F to the R. So certainly B will sit inside of GRP. Okay. So I want to define the following. So for a weight, I want to define ER. Okay. So there's a hat and a prime on top of this. And this is going to be induction from B to GRB of lambda. All right, so this is kind of an enhanced version of the Baby-Verma model. And now I'm going to do a co-induced one. So this is ZR hat. Okay, this is without the prime. And this is going to be the co-induction from B to GRB. Okay. Now, the good thing about this is if I take this module and if I restrict it down to GR, so GR also sits inside of GRB too, then this is induction from BR to GR. So the idea is that this module has more structure, but when you restrict it down to the Frobenius kernel, This is the old sort of baby Varma module we looked at before. So these are kind of enhancements of this. And similarly for this one too, you restrict down to GR and get co-induction from BR to GR. Okay, now another, what we can also do is we can construct some other ones too. So let me do that. Let me just write it over here. It just makes more sense. So if I take ZR prime lambda, and if I can also restrict it down to GRT. So remember, GRT is inside of GRB. And just by using the definition. So if I take this one, I restrict this down, I can write this as follows. Induction from GRT to BRT of lambda. Okay, so you can imagine what BRT is. I'm not going to write it out. You take the Frobenius going from the Borel to the Borel. Take the rth iteration, which goes from B to B. Take the inverse image of T, and then you get BRT. Okay, and similarly, you get GR hat lambda when restricted down to GRT. Co-induction, BRT, GRT. Okay, so these are just sort of geometry versions of the objects that we defined before. Great. Okay, so now we have a proposition. And so it turns out that these modules are sort of translation invariant, meaning that if I take lambda plus p to the r times some weight, then I can just pull the p to the r out by the tensor identity. And the modules, if I restrict them down to GR, are the same under this translation. Okay, so here's the first tip. If I take ZR of lambda plus p to the r mu, so lambda could be any weight you want. Do I have on this? I guess I better put a hat on this. Let's just put a hat on this. Lots of adornments here. ZR hat lambda tensor PZR. All right, and then two, if I do a ZR hat prime of the same thing, this is equal to ZR prime lambda tensor PZR. And okay, so maybe this is 1, 2, and this is 3. And what's the character? Well, the character of the ZR hat lambda turns out to be the same as the character of ZR prime hat lambda. Lambda times the product overall positive roots of 1 minus e to the PR alpha over 1 minus e to the minus, I should have minus alpha. Okay, so let's see why these are true. Okay, so here's a proof of this. Okay, so let's look at 1 and 2. So notice that let's just take 1 for example. So let's say I take, or actually let's take this one down here. So if I take ZR cap prime lambda plus PRV. Okay, so let's write the definition now. So induction from B to GRV of lambda plus PRV. Okay. Now, when I write lambda plus PRV, I could actually think of that as a tensor product between two modules. So this is going to be induction from B to GRV of lambda tensor to GRV. Okay. Now, when I take P to the R mu, this is actually a module for GRV. P to the R mu is a one-dimensional module for GRV. Okay, so what's the reason for that? Well, first of all, this is a module for B, clearly. Right? So let's just kind of write this down. So if I have GRV here, let's see. So I guess I have a map to the quotient. Okay. So this is the twisted R times. Okay, so another way to think about it, this is V over VR. Okay. So this is a one-dimensional representation for B over BR. And so I can just pull it back to the action for BR like GRV, because this is just a quotient now. Okay, so GR actually acts trivially on this. All right, so this is a GRV module, so now I can just use the tensor identity. So this is isomorphic to induction from B to GRV, lambda, and then I can pull the whole thing out. Okay, so that's how I get this. Just use the tensor identity. Okay, any questions on this? All right, so that proves 1 and 2. And then for number 3, I can just write out a proof. And the idea is that we just use the sort of the PVW theorem to get this. All right, so let's do that. Okay, so all right, so let's do this one first. The character of Z R lambda. Okay, so do I want to add on there? Okay, so this was the induction, this is the co-induction. Put the add on there. Okay, so this is going to be isomorphic as a vector space to disk GR tensor lambda. Okay, so we saw this before that, you know, you can sort of write this in terms of just the R which kind of sticks out, tensor lambda. It's a tensor induction. Okay, so what's the character of this? So actually, I just should write this first. And so the character, well, it's the character of lambda. Okay, we know that. So that's E lambda times the character of distribution of UR. Okay. But remember what dist of UR was. It contains these sort of elements of the universal enveloping algebra, which go to P of the R minus 1. Right? So this is going to be equal to lambda. And so what does an element look like? Well, if I take a root, so I take a product, I get 1 plus e to the minus alpha plus e to the minus PVR minus 1 alpha, something like that. Okay, so for every root vector, I have to take, just possible sort of exponents right up to PVR minus 1. Again, I take the product, that's how I get the character. All right. And then, you just use your geometric series sort of identity here to get this identified. So this is just going to be E lambda product alpha implied plus 1 minus PR alpha over 1 minus E minus. Okay, so that proves you the character. Any questions? All right. Now, the category GR and GRT are very close to one another in the sense that, one's just kind of the graded category of the other one. So the irreducibles you can get fairly easily pass from one category to another. And we'll talk about that in a moment. But first, let me prove the following theorem. So let M be a GRT model. So the theorem says the following are equivalent. So 1, M is an injective GRT module. Okay. And 2, M is an injective GR module. Okay, so if you have a GRT structure ready, then if it's injectable over just GR, it has to be injectable over the whole thing. All right, now Janssen has a proof in his book, but I have a different proof. So let me present a different proof. All right, so here's how it goes. All right, so first of all, as I mentioned, GR sort of sits inside of GRT as a normal subgroup scheme. So you have GR normal inside of GRT, and the quotient is going to be just this T to the R. So GRT factored by GR is, it's basically a copy of T, but it's sort of twisted like the Frobenius orthogonals. So in other words, it's just T over TR. All right, now whenever you have a situation like this, when you have like a normal subgroup inside of a group, you have a spectral sequence, the Lindenhoff-Schelzera spectral sequence. So group, we're going to apply Lindenhoff-Schelzera spectral sequence to this situation over here. All right, so the idea is the following. So let's say N is another GRT module. Then we have the E2ij xi. So it's a spectral sequence where the E2 term sort of starts with the cohomology for the base, which is the quotient over here. So T over TR. And I might as well just put the trivial module here. Xj. This one's the case. And then this converges to xi plus j of GRT. Okay. All right, any questions on this? Sort of a standard construction. You can do this by using the growth and deconstruction if you want, or you can actually sort of form a double complex and then take the spectral sequence that way. All right, now we're in fairly good shape. So we have the spectral sequence. So which direction do we want to prove first here? Okay. So let's assume 2 is true. So assume 2 is true. So this is 2 implies 1. Okay, so let's assume that M is an injective GR module, right? So what this says is that this cohomology is going to be 0. Okay? So this implies that xj of gr of nm is 0 or j bigger than 0. Okay, so that means that the spectral sequence collapses. Right. So spectral sequence collapses. And what do we get? Well, we get that x I of PVR of K GR of NM is isomorphic to x I GRT okay. All right, now we're not quite done yet. We have to use the fact about the torus. So over the torus, all modules are completely reducible. So there's no extensions between modules. So since modules over the torus TR are completely reducible, this implies that the higher x vanish too. So xi of tr of k gr of nm. This is equal to 0 for we ask. Maybe David knows. So for which I is this going to be 0 for?
For all I greater than or equal to 1?
Yeah, that's right. I'll just say greater than 0. Exactly. That was a qualifying example. All right, so now, okay, so this is going to be 0 for I bigger than 0. And so this is going to be 0 for I bigger than 0 too. So that means that xi of GRT of NM 0 for I bigger than 0, which means this holds for any single n you want, right? So that means that M is injected. Everybody good with that? All right, now what I need to do next is I need to look at the other direction. So I'm going to use the spectral sequence again, but sort of in a different way. All right. So this is now 1 implies 2. All right, so I'm going to use a fact, and this fact I'll actually state later. So the simple, let's see, is that what I want to do? Let me see. Yeah, so let's see, I want to, so one was inject over GRT. Yeah. So here's the idea. Okay, so the idea is that so let me just state it this way. Okay, so first of all, the simple GRT modules are form. I'll do it this way. LR lambda tensor PR sigma. Okay. Where lambda is in XRT and sigma is just any weight. So basically, you just take the GR modules and you tensor them by a one-dimensional representation. Okay, so I'll actually state this later on. Okay, so now what I'm going to do is I'm assuming that I have projectivity over here. So let me say that this is a simple GR model. So you sort of get them by taking simple GR modules and tensoring by these one dimensions. Okay, so what I'm going to do is I'm going to plug in n with the simple module like this. Okay, so let n be equal to LR lambda tensor PR sigma. Okay. All right, now I have the spectral sequence over here, but this turns out to be a Grothendieck type spectral sequence. It's first quadrant, and you have a 5-term exact sequence. Okay, so use what's called 5-term exact sequence. So I'll write out the 5 terms. So 0, E2 1 0, 1, and this is going to be equal to E2 0 1, and this is going to go to E2 2 0, and then so this is a 5-term exact sequence. Now, all we have to do is we have to look at X1 to show, to actually show that it's injected. Okay. All right, so the first thing we can say is that when I plug this module in over here, we're assuming that M is injective as a GRT module. Right? So remember, let me just say this, assume M is injective as a GRT module. Okay. All right, so automatically, that means that X1 is going to be 0. That's E1. And then X2 is going to be 0. So automatically, I have 0 here, and I have 0 here. Okay.
So what are the E1 and E2 with no superscripts?
So that's X1 of GRT and E2 is X2 of GRT, and it's the button, right? Yeah. All right, so I get 0 here and I get 0 here because of this hypothesis. All right, now I said that all modules over TR are completely reducible. Right? So whenever I have an X1 of TR, it has to be 0 too. So this follows from, so this one is 0 here, And this one is 0, 2. Because I have an x1 of TRK of, whatever, doesn't matter. All right, so I got zeros in a lot of places. And so now I have this. Okay. So let's analyze what that is. So therefore, E2, 0, 1. That's Hom TR. Okay. X1 GR. Now I'll plug the N in. So this is going to be LR lambda tensor PRV. PR sigma. Okay. So let me see. I close off of the parentheses here. Okay. So this is it. All right. Okay. Now GR acts trivially on PR sigma. So I can pull it outside of the cohomology here. And this will be minus PR sigma, and then I can move it over to the other side. So this whole thing is going to be equal to Hom PR. And I can take PR sigma over here. And I can look at X1 GR LR lambda. Okay. Now, this is 0 for all PR sigmas. And the irreducible representations for TR are the form PR sigma. Right? So, I mean, this is completely reducible. This module is completely reducible. It's going to break up into irreducible representations. So I'm saying the Hom between any irreducible representation in that module is going to be 0. So this happens for all PR sigma. So that means that this X has to be, the X tier has to be 0. Okay. And this happens for all irreducible representations, which are restricted. All right. So therefore, M has to be injective as GR1. So, spectral sequences are good animals to have around. Okay, any questions on this? Okay, good. All right, so let me just state a few facts. So these are things that you've seen before for the GR category. So here's a proposition. So let lambda be a weight. Then 1. When I take CR hat lambda, and if I restrict it down to the BRT, this is the projective cover of lambda. And the injective hull. The one-dimensional dimensional representation, lambda minus 2, PBR minus 1 rho. Okay, again, rows have some of the positive roots. Okay, so we've actually seen this theorem before for BR, I believe. So if you believe, I mean, this is something I stated before for BR. So all I'm doing is I'm just putting an additional action of the torus on, and it grades the module. And you have to look at all weights instead of just restricted weights in that case. Okay, so 2. Z are half prime, lambda, when I restrict it down to BR plus, is projected cover of lambda minus 2, BR minus 1 rho, and the injected wall plan. Okay, so similar to all right. Now, as you can imagine, we classify GR modules by using these baby Verma modules. So you can just do the same thing. You can classify, GRT simple modules by just using these modules also. So I'm just going to summarize how to do this. And it's the same proof that we went over with like the H0 lambdas and the same idea. Okay. So let me give you a summary. So summary the classification is simple, the GRT model. All right. Okay, so here's how we do it. So the first thing is, if I take the socle, the BRT plus socle of CR prime half lambda, this turns out to be lambda, and if you take the fixed points under U plus, I guess it's U plus. Then I get lambda. Okay, so this is similar to what we did with the H0s. So basically, these things have, because you have a T action here, right? They have one-dimensional weights, one-dimensional highest weight, and the highest weight is lambda. Okay, and this highest weight space is the U plus invariance. So now the second thing was we just let LR hat lambda. Okay, so remember we're in the GRT category, so I have to put a hat on everything. And this is just going to be the socle in the GRT category of this gadget here. That's the induced module. Okay, I mean just like before. All right, so you do the same proofs, and so here's some properties. So each simple GRT module is isomorphic to LR hat lambda for some. Okay, now before with GR, I looked at restricted weights, but now I have to look at all weights. Because so we've kind of kept it, instead of letting the weights sort of collapse mod P, we don't let the weights collapse mod P. Right? We just look at all weights. Okay. All right. Now, so what's another property? So another property is if I take LR hat lambda, let me just say it this way. So if I restrict this down to GR, this is isomorphic to LR lambda. This is for all lambda in X1T. Okay, so if your weight is in the restricted region and you restrict this module down, you just get the GRT irreducible. Okay. And then these modules are translation invariant. So if I translate by, or just multiply the weight by PR lambda, then this turns out to be LR lambda hat tensor sigma. Okay, so you can always pull out any P to the R something outside and multiply. And then from this, it's pretty clear that if you take something like this, and if you restrict it down to GR, this is the same as LR lambda. For all lambda. Okay. So this happens, you can also do this for GRB modules. So one can also do this. To describe GRT modules. All right, so let me draw you a picture here. We're going to be a little bit more daring. So, okay, so here's minus rho here. So now what I'm going to do is, let's see if I can get this right. So I think it's this. Okay. So this is a B2 diagram. Something more exciting here. So this is the B2 system. Let me draw it a little bit better. Okay. So what I described down here is for the B2 system is the restricted region. Okay, so this whole thing is a restricted region. So this, I should just say this whole part here, this is X1T. Now, the idea is, we know that irreducibles are indexed for GR or G1 are indexed by things in the restricted region. Okay. Now, what I need to do is for GRT, I'm just replicating the restricted region sort of as much as I can. So here's a translation over here. So there's this one, there's this wall up here, okay, and then there's this one here, and then as you can see, there's this thing. Let me, we're out of room. You can see what I mean. Okay, so notice that the restricted region here is just translated up to here. Okay. And if I take a weight here and a weight here, this is just it's like the weight down here plus P to the R times something or P times something. So if I take an irreducible here and an irreducible here, then they're the same as GR modules. Okay, not as GRT modules, because I have to keep track of the weights. Okay, but in terms of GR modules, they're the same. Here is translation here. Now let me just kind of draw that in. So here's lambda here. Here's lambda plus P times sigma. Okay. So here, this LR lambda hat is isomorphic to LR tan lambda tensor P sigma as G1 modules. So this should be a 1 and this should be a 1. Okay, so does that make sense? So what you do is you take the restricted region and you sort of, replicate it across, the entire Euclidean space, right? And so in some ways you're not really getting anything new. You're just able to put gratings on modules. And that's what you're able to do. Okay, any questions? This idea goes back to Janssen, and you don't want, whenever you work with characteristic P, let's see, whenever you work with characteristic P, one of the things you don't want to happen is you don't want to have to work mod P. You want to work with like integers, and so this allows you to actually use integers and use weights like you normally would. Okay. All right, so I'm going to state a theorem and then I'll prove it next time. This theorem turns out to be extremely useful for what I'm working on now, actually. So. Proposition. All right, so I'm going to take any weight here. Then there exists an isomorphism of G modules. And so at first you might think, okay, does this have any worth? And it turns out the answer is yes. There is some like merit to this proposition. And so we don't know very much about HI lambdas. So we know it's the higher right derived functors of something. So it turns out that I can actually go up from GRB to G. And then over here, I can just take one of these induced modules, Z prime lambda. So normally I have to induce from B to G. But now I can induce from one of these sort of baby Verma models to get up to the whole. Okay. So remember that ZR prime at lambda induction from B to GR. Okay, now why is this useful? Well, it's useful because, if you know something about the composition factors for the baby Verma modules, then it allows you to put certain filtrations on these HI lambdas. In particular, if I is equal to 0, then it allows you to actually show sometimes that the induced modules have what are called good P filtrations, which I'll get into later on. So this actually turns out to be a very useful theorem. So what I'll do is I'll prove this proposition next time, and then I'll actually introduce good P filtrations to you and show that under certain conditions you can actually construct good P filtrations by knowing certain vanishing conditions on weights. Actually, not vanishing, certain inner product conditions on weights. Okay, so let me stop here. Are there any questions? Okay, good. So we will continue on Friday.
See you guys.
Okay, we'll see you.
Have a good day.